here is our simple harmonic oscillator. Now, if we could look at the shadow of a simple harmonic oscillator, it might look something like this. Here's the shadow. You know, you see it reaching zero and maximum velocity right at the middle point there is shown. And we have this, what looks like simple harmonic motion. But in fact, it's not simple harmonic motion that we're showing here. This is something that will come close to simulating it, which is something turning, rotating, and we'll look at the shadow of that thing. And what's interesting is circular motion can be used to describe the mathematics of simple harmonic motion. They're related. The shadow. Now let's take a look at how circular motion relates to simple harmonic motion. It allows us to find a formula for the period of the mass on a spring. Now, as our body is turning around and rotating, light is shining and the shadow is shown on a screen there, as you see. Now, that shadow, of course, at the very top is zero. It stops because we're only concerned with the vertical component of that velocity. Now look, there's the arrow for the speed, but if we take the vertical component of that speed, that is what is representing the shadow on the screen. At that point, we see that we have the maximum speed, and the shadow, of course, has maximum velocity. Here the velocity is now slowing, and it's only the vertical component we're concerned with. And finally, at the bottom, we would see a zero velocity. The vertical component of that is zero. And so that's how this describes this motion, this shadow, this thing turning. The vertical component is what we're using. Now, what is the orbital speed of something going in a circle? And it's 2 pi r over t. Now, that's something we've done before. Just remind yourself of it. And that's the radius or the amplitude of our simple harmonic motion. That's the amplitude. So let me just rewrite that with the amplitude, substituting that in for r. And the orbital speed is 2 pi a, r is maximum amplitude, over the period. Now let me rewrite this in terms of period. And period is equal to 2 pi a over v. Now, let's go back and remember what happened. The period of the turning record is the same as the period of the shadow on the wall. Well, we know if we look at the shadow on the wall, if you remember, 1/2 Ka squared equaled 1/2 m v max squared. Well, v is the orbital speed of that turning thing. That's the orbital speed. It's a constant speed. And so we have a squared over v squared. Look at that equation. A squared over v squared. The halves cancel. A squared over v squared equals what? M over k. Now, if I want to get rid of the squareds, I just take the square root of both sides. So a over v is equal to root m over k. And so the period can be represented as 2 pi times root m over k. Now you need to memorize that formula. 2 pi root m over k is the period of a simple harmonic oscillator. K is the spring constant. M is the mass. An easy equation to remember and easy marks. So let's review about the simple harmonic motion and simple harmonic oscillator. We know that we'll call that the already extended spring at rest as our 0 point. And therefore we can consider as the energy now, once we got it oscillating, that's the maximum velocity as it passes through that point, and the energy is all kinetic energy, 1/2 mv squared. At maximum extension, all of the energy is stored elastic energy in the spring. The velocity is 0, so the energy then is 1/2 Ka squared. And we can then say, 1/2 mv squared equals 1/2 ka squared, which becomes a useful formula to solve for unknowns in simple harmonic motion. And we can also say that the period of a simple harmonic oscillator, a mass and a spring, is 2 pi root m over k. Now, these are good equations to memorize. You have to have them memorized. They're easy marks on the test. And I would suggest now you go to that chapter on simple harmonic motion in the book and try some of the problems, and it should all make sense now. But there's one more thing. A pendulum will be close to simple harmonic motion for small amplitudes. And I will tell you this formula. This one also needs to be memorized. Very simple to manipulate. Very simple to use and memorize. Easy marks, because they just ask you to solve for an unknown. Period is 2 pi root L over G.